Welcome back to our lectures on acids and bases. In this lecture we're going to be talking a bit about acids and bases in industry, and we're also going to be doing acids and bases and talking about pH. In your textbook it's page 227 to 230. So in this lecture you'll be able to define what a neutralization reaction is. You'll be able to perform calculations involving hydronium ions. You'll be able to interpret the pH scale, and you'll be able to perform calculations involving the pH scale, basically calculating pH. So one of the reasons we talk about acids and bases is because they're so important. If we just look at even sulfuric acid, you can determine how strong a country's economy is based on the amount of sulfuric acid it uses in its industries. So sulfuric acid is involved in all of these industries, in pharmaceuticals, petroleum, explosives, dyes, paints, fertilizers, rayon fibers, and so on. It's such an important acid that, like I said, you can judge the strength of a country's economy based on the amount of sulfuric acid it uses. So acids are really important in terms of everyday life. They're used in almost every facet of life that you can think of, and because they're used in industry, it means that there can be industrial accidents, unfortunately. So we're also going to learn how to deal with acid spills. There's basically two ways to deal with an acid or base spill. The first way is to dilute it. Add water. If you have small spills that are really acidic or really basic, then all we need to do is add water to dilute our acid or base. Since pH is determined by concentration, as we add water, the concentration of our acid or our base is going to be reduced. So using this method, we can actually get quite close to a pH of 7 or to neutral, and it's a good way to neutralize a small acid spill. So flushing it with water is good for small spills. For larger spills, we know that acids and bases react with each other. Acids produce hydronium ions, bases produce hydroxide ions, and when the two get together, they react to form water, and water is a pretty safe product. So for larger spills, sometimes it's easier to add an acid or a base depending on what you've spilt. If you spilt an acid, you're going to add a base. If a base has been spilt, you would add an acid to neutralize that hazardous material. So for neutralization, it can be defined as an acid reacting with a base. Every time an acid reacts with a base, two products are formed: a salt, or some sort of ionic compound, and water. So a salt is any neutral ionic compound. We think of salt as being NaCl. Well, that's just an example. So the sodium chloride, that is just an example of one salt. It's just the most common salt that we know of. For any reaction, so here we have a reaction between, here's our acid, here's our base. The products are a salt, so calcium bromide, right? This is an ionic compound and it's neutral, and water. So this is a neutralization reaction. Now, neutralization reactions can be used, for example, to monitor swimming pools. Swimming pools have to be kept at a certain acidity, and by doing a neutralization reaction with a sample of swimming pool water, we can determine how acidic that water is. They're also used to test pharmaceuticals. Obviously, you don't want pharmaceuticals that are too acidic or basic. They can become dangerous. So one way, or one relationship we know between acids and bases is with pH. So when we look at pH, we know that if the pH of a solution is less than 7, we have an acid. Another way to say that is the concentration of hydronium ions is higher than the concentration of hydroxide ions in an acidic solution. For neutral solutions, the pH is equal to 7. Or another way to say it is that our hydronium ion concentration and our hydroxide ion concentration are equal. There's an equal number of each, and this comes from this dissociation reaction up here. If you have pure water, occasionally water molecules will bump into each other. So you have a pure sample of water, there's nothing else in there. Water molecules can bump into each other. If they bump into each other the right way, they will occasionally form hydronium ions and hydroxide ions. One water molecule will steal a hydrogen ion from another water molecule, and so they'll become hydronium and hydroxide ions. And since it's on a 1-to-1 ratio, for every one water that gains a hydrogen ion, one water has to lose a hydrogen ion. The concentration of each is always going to be equal. So that's why water is a neutral solution. It has an equal number of hydronium and hydroxide ions. For basic solutions, we have the last case where our pH is actually greater than 7. So the higher the pH, the more basic the solution. Another way to say that is our hydroxide ions have a higher concentration than our hydronium ions. So there's two ways we can actually classify our solutions, one based on pH, the other based on the comparing concentrations of hydrogen ions, or I should say hydronium ions, to hydroxide ions. Now it also turns out that when you measure the concentration of hydroxide and hydronium ions in pure water, their concentration turns out to be 1.0 times 10 to the negative 7 moles per liter, which is really, really small. It's much smaller than any of the numbers we're used to dealing with, times 10 to the negative 7. If we were to write this out longhand, it would be 0.1234567 moles per liter. So a really, really low concentration, which should make sense because water molecules are happy being water molecules. They aren't often going to trade hydrogen ions. So it doesn't happen very often because they're happier being water molecules. One thing we should notice is that pH of 7, and it's not just coincidence, that matches the exponent on our concentration. And so this is actually a relationship between pH and hydronium ion concentration. So pH was developed because of the awkwardness of using these concentrations for acids and bases. For example, we saw that water concentration, the concentration of hydronium ions was 1 times 10 to the negative 7th, which is a really small number. And for other acids and bases, they're going to be equally small decimal answers. So a system was developed to express these concentrations in a more convenient way. So it was developed for measuring the acidity of any solution, and it was developed by Soren Sorensen in 1909. And basically what he did is he expresses the pH based on the power of 10. So if something has a concentration of, say, if the concentration of H3O ions in a solution is, say, 1.0 times 10 to the negative 8, then the pH is going to be that 8. That exponent on that 10 is going to be your pH. So in this case, this describes a basic solution because our pH is above 7. Likewise, if we had a solution where the concentration of hydronium ions was equal to, say, 1.0 times 10 to the negative 2, the 2 is our pH. So in this case, this would be an acidic solution. So this solution up here would have a pH of 8. This solution would have a pH of 2. And it's much easier to talk about a pH of 8 or a pH of 2 as opposed to the concentration of hydronium ions is equal to 1.0 times 10 to the negative 8 moles per liter. So it really does simplify how we're going to talk about things. And I shouldn't be lazy. I should have put down moles per liter for each of these concentrations. So in order to do this calculation, it involves the use of logarithms, which is basically for us, it's a button on a calculator. So if we want to calculate pH, we do it with this formula here. The pH of a solution is equal to the negative log of the concentration of hydronium ions. So, and this is where the negative logarithm of the pH, if we have a concentration, we can also go backwards as well. So, one thing we should notice is that on the pH scale, 1 unit on the pH scale represents a 10 times increase or decrease in acidity. So for example, vinegar is 1,000 to 10,000 times more acidic than milk. And so let's see what that means. If we find milk, milk has an acidity or a pH of about 6.4. Vinegar has an acidity of 2.4 to 3.4. So there is if we just do subtraction, 6.4 minus 2.4, that would be 4 units. And each unit is a 10 times increase, so 10 to the power of 4 times difference. And that's how we get 10,000 times more acidic. If it was 3.4, the 3.4 is only 3 units, so that's how we get our 1,000 times more acidic. So for every unit on our pH scale, we increase acidity or decrease acidity by a factor of 10. So now we're going to do some calculations. So we're going to get pH from our concentration of H3O. There's our formula. We can also work backwards. If we have the pH, so for this one, we use this when we have the concentration of H3O, the concentration of hydronium ions. We use this one when we have the pH. And we'll do some examples. In terms of significant figures, the numbers of digits following the decimal point is how we calculate our significant digits. And I'll just give you a reference in our textbook as well so you can read about what I'm talking about here. So in your textbook, for this pH, for this number of significant digits, see page 773. And so on page 773, or actually it starts on page 772, and so it describes how to calculate significant digits for using logarithms, and there's also some examples on page 773. So try the practice problems on page 773. And so just to make sure you're getting your number of significant digits right when you're doing pH calculations. So here we're going to try an example. So determine the concentration of hydronium ions when we have a pH of 6.3. So we have the pH is equal to 6.3. We're looking for the concentration of hydronium ions. So the formula we're going to use is going to be the second one. The concentration of hydronium ions is equal to the inverse log of negative pH. This is the same as on some calculators, which you'll see instead of an inverse log, another way to say it is it's equal to 10 to the negative pH. That is the inverse of a logarithm. If you're confused with the terms, that's okay. It's a Math 30 thing, but in terms of our calculation, we're just going to memorize a formula. So 10 to the negative pH, or the inverse log of pH. So, and if you're having calculator problems, what I would suggest is either contact the TA for the class or myself, and they will be able to help you through the calculator problems. But what you're looking for is usually a second function or an inverse function, and it's going to be a second function button on your calculator, and it's usually the second function of the log button, the LOG button. So on our so we'll plug in our numbers here. I'll just write it as 10 to the negative 6.3. That's the inverse log. On our calculator, it's usually a second function log, and then you can enter your negative 6.3, and we get 5.01187 blah 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 blah, and this is moles per liter. Now, for significant digits, we take a look at our pH, and for pH, it turns out that only the digits behind the decimal are counted as being significant in terms of how many digits we use in our answer. So this pH has one significant digit, so our answer is going to have one significant digit. Oh, and I forgot, so times 10 to the negative 7 moles per liter. Sorry about that. And so our final answer is going to be 5.0 times 10 to the negative 7 moles per liter. So one thing to note for this example, with scientific notation, the best we could do is 2 sig digs, even though we're only allowed 1. And what I can say is that none of the other examples or test questions will have this problem. You'll always be allowed to report the right number of significant digits. So we'll try another one here. We want to determine the pH of a solution where we have a concentration of hydronium ions of 3.77. So we've been given the concentration of H3O+, we want to find pH. So because we want to find pH, we're going to use the first version of our formula. We're going to say pH is equal to the negative log of 3.77 times 10 to negative 9. And this is moles per liter. Note that once we're done our logarithm, it loses its units. So pH doesn't have any units associated with it. And for our calculator, hopefully you can figure this out. If not, be sure you contact the TA. And so we go negative log 3.77 times 10 to negative 9. And you should get a pH of 8.42365, blah 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 blah. And because when we look at our original number, we need 3 significant digits. So there's 3 significant digits for our concentration. We need 3 significant digits for pH. And for pH, only the digits after the decimal are counted as being significant. So there's 1 sig dig, 2 significant digits, and so 3 significant digits. That 3 would round up to a 4. And this would be the pH for our solution. So we'll give another one a try. Here we have a hydronium ion concentration, or we're looking for the hydronium ion concentration, and we're given a pH. So since we have pH, we're looking for the concentration of H3O. And so we're going to use our concentration of H3O is equal to 10 to the negative pH, or the inverse log of pH, negative pH. And so we can plug this into our calculator, negative 2.567. And so inverse log negative 2.567, and we get a concentration of 0.0027 and 1. Now, our pH has 3 significant digits, so we need 3 in our answer, moles per liter, and we should express it in scientific notation, so we're going to move our decimal 3 spots over, so it's going to be 2.71 times 10 to the negative 3 moles per liter. And that's our concentration of hydronium ions. This should make sense. Our concentration of hydronium ions is relatively high, and our pH tells us that this solution is going to be an acid. So the pH says it's going to be an acid. Our concentration is relatively high, especially when we consider that water, just all by its lonesome, has a pH equal to 7, which is that 1.0 times 10 to the negative 7 moles per liter for its concentration of hydronium ions. So when we compare the two, we can see this solution said it was acidic according to its pH, and it turns out to be acidic when we do our calculation. So we're probably right with our calculation. So all I'm doing here is just double checking my work and making sure that my answer makes sense with the question. So for the next one, we're going to calculate pH. So we're looking for pH. We've been given the concentration of hydronium ions. 0.00025 moles per liter. And so we're going to use the first version of our formula, where pH is equal to the negative log of 0.00025 moles per liter. And when we're finished, we get a concentration of, or a pH of 3 point. And now before I finish, the question has two significant digits, so we need two significant digits for our pH, so 3.60. Remember, for pH, only the digits behind the decimal count as being significant, so our pH is 3.6. Okay, so now we'll get into ones that are a little bit more than just straight calculations in terms of moving from one to the other. We want the pH of a solution made by dissolving 1.45 grams of hydrogen iodide in 500 milliliters of water. So we have to figure out, well, what the heck do we know? And what we'll start with is we have hydrogen iodide being put into water. Now, hydrogen iodide, if we take a look, is a strong acid, which means it dissociates 100%. So, in water, hydrogen iodide, when we put it in water, it reacts with water molecules to produce the iodide ion and H3O+. And so when we're given a compound, an acid or a base, we're going to write down what happens in water, and that way we have a place where we can start putting in numbers. When we put something in water, it becomes a solution. So I'm going to put the volume underneath my hydronium ions, just to remind me that that's the volume I'm going to use for concentrations. They gave us a mass of 1.45 grams, and it was the mass of hydrogen iodide. What we want is pH, and I'm just going to write the pH underneath my hydronium ion because that's what pH is related to. pH is related to the concentration of hydronium, not the concentration of our acid. The concentration of our acid compound or our base compound is going to be different sometimes than the concentration of our hydronium ions. So to solve this problem, we're going to make a little bit of a plan first. In order to find pH, we need the concentration of H3O+. So we've got to find that first. In order to find the concentration of H3O+, I'm just going to use a concentration symbol here because we need to find that. In order to find that, we're going to need to use our chemical equation. And now this goes back to some of our dissociation equations with finding the concentration of ions. For every 1 mole of hydrogen iodide used, we get 1 mole of hydronium ions. So we can use our mole ratio, and find the number of moles of hydrogen iodide. So to find the concentration of H3O, we're going to have to find the number of moles of hydrogen iodide. Once we do that, then we can find pH. So we actually got to find a couple of things here. First, to find the number of moles of HI. So that's where we'll start. Number of moles of hydrogen iodide. In order to find that out, we're going to use our molar mass formula. And so the number of moles is going to be equal to mass over molar mass. And so we need molar mass. So we'll write it down up here. The molar mass of hydrogen iodide of 1.01. So the molar mass of hydrogen iodide is 127.91 grams per mole. That's a 9. And so now we can start our calculations. So 1.45 grams divided by 127.91 grams per mole, and we get 0.0113 moles. Now we can use our mole ratio. So the number of moles of hydronium ions is our 0.0113 moles times our mole ratio is 1 to 1. So the number of moles doesn't change, but it's nice to write that mole ratio down so that we don't forget to use it. And so from that we can find the concentration of, now big C, or if you like, both of these symbols mean the same thing, concentration of H3O ions is equal to N over V, our concentration formula. So we get the number of moles is 0.0113 moles. Our volume of water, make sure it's in liters, 0.5 liters. So our concentration is 0.0227. In my calculator, I have used the full number the whole time. And now that we have concentration, now we can find pH. pH is equal to the negative log of our concentration, or the concentration of H3O plus ions. And so I'll plug my numbers in up over here. So pH is equal to the negative log of 0.0227. And so our pH is 1.645. And the reason I have 3 digits behind the decimal here is because I have 3 significant digits in my question. So both my numbers have 3 significant digits, so my answer has to have 3 significant digits. So there's the pH of our solution of hydrogen iodide. So it takes a little bit more work. The biggest trick to these problems is really understanding the steps you need to follow in order to get the answer. Get that equation written down, and then make a plan by kind of working backwards. Figure out what you need to get the pH, and then from there you can figure out what you need to get that first step done. So here's another example. The pH of a stomach acid solution is 1.5. We're going to calculate the mass of hydrogen chloride dissolved in the sample. So this one, same thing. We're working with hydrogen chloride. So we're working with another strong acid, which means it dissociates 100%. So we have HCl, and it's a gas at room temperature, plus water. So we're in stomach acid, so we know it's been dissolved in water. Reacts 100%, so a one-way arrow, and we get chloride ions when that hydrogen chloride loses its, or when that hydrochloric acid loses its hydrogen ion, plus H3O plus aqueous. And now that we have our reaction, we can figure out where to put some of these things. So we have a 25 milliliter sample of stomach acid. And so that's related to concentration. And for concentrations and acids, we're going to put our concentrations, or sorry, it's a volume, my bad, it's a volume. But we're going to put it with our hydronium ions. So the volume is 25.00 milliliters. And they've given us the pH, and pH is always related to the concentration of hydronium. So we're going to go 1.50 is our pH. They want the mass of hydrogen chloride. So there's what we're trying to find. Since we're looking for mass, we only have one formula with mass, so we need molar mass as well. So the molar mass, 1.01, plus the molar mass of chlorine is 35.45. So our molar mass is going to be 36.46 grams per mole. And now we have the molar mass, and so now we got to think of a bit of a plan. In order to find the mass of our hydrogen chloride, we need to find the number of moles. So we've got to find the N of HCl. In order to find the N of HCl, we're going to use our hydronium ions, and we're going to first need our concentration. So the concentration of H3O is what we're going to need first. And we can get that by using our pH. So we know that the concentration, so now we have a bit of a plan. The concentration of H3O plus is equal to 10 to the negative pH. And so we'll plug in our pH, 10 to the negative 1.5, or the inverse log of negative 1.5. And so the concentration of hydronium is 0.0316 moles per liter. Again, I'm saving that full value of my calculator. Now I can find the number of moles of H3O plus. And we're going to use our concentration formula. So I'm just going to write that down over here. Concentration is equal to N over V. We want N, so N is equal to CV. So concentration times our volume. Our concentration is the 0.0316 moles per liter, and our volume is 0.025 liters. Always make sure our units match. So we're going to multiply by 0.025, and we get 7.9 times 10 to the negative 4. So 7.9, I'll write down the 1, times 10 to the negative 4, and this is just moles. Now we can use our mole ratio, so I'll bring the question up over here. Now we can find the number of moles of HCl, which will be our 7.91 times 10 to the negative 4 moles times our mole ratio is 1 to 1. So the nice thing about these acid-base problems is our mole ratio is always going to be 1 to 1, or almost always. And so the number of moles of hydrochloric acid don't change, or hydrogen chloride. Now we can find mass. The mass of HCl, and we're going to use our molar mass formula. So molar mass is equal to mass over moles, which means mass is equal to molar mass times moles. So it's equal to molar mass times moles. Our molar mass is 36.46 grams per mole. And our moles is the 7.91 times 10 to the negative 4 moles. And so we end up with 0.0288 grams, and I would convert that to milligrams, so we're going to multiply it by 1,000, and so it would be 28 point, or we'll just go with 28, and I'm going to stop there. Nope, yeah, stop there. 2 sig digs, 28 milligrams. And the reason there's only 2 sig digs is because our pH only has 2 sig digs. And actually, sorry, I should go back. That has to be rounded up, so it's not 28, it's 29. Because of that 8 behind it, so 29 milligrams. Okay, so last example. A small sample of hydrochloric acid with a pH of 3 spills on a lab floor. Water is added to the spill to determine the maximum pH possible of the diluted solution. So here's just a thinking question. As we add water, the pH is going to increase. So, and this should make sense. I mean, we have something with a pH of 3, and we're adding something with a pH of 7. So this is because H2O has a pH of 7. Now the question is, what's the maximum possible pH of the diluted solution? And so as we dilute, the highest this pH could get would be about 7. We're never going to get above 7 because things with a pH above 7 are basic. So since we're not adding a base, we're only adding water, the maximum pH of this dilution would be almost 7, would be 7. And that's simply because that's the pH of our water. That's the highest the pH can get because that's the maximum pH we're adding to our solution. So there are a few examples on page 230, and I'll see you in the next lecture.